In this video we are going to study how to use a camera in order to perceive useful information from the environment, especially for a street. This is the scenario where we are going to work. We have a robot in the street and we have a camera that we will use for the lane detection, and we will try to detect the dashed yellow line on the floor, and we will have a differential wheel drive robot. Trying to sketch the horizontal view of the robot, we have the floor that is completely flat, and we see the robot from the side. And attached to the robot we have a camera. This camera is tilted to the ground, so we can see the objects over the floor, and this camera has a field of view that we represent by the green lines. An overview of all the perception problems will start with a robot that detects a point on the floor, and then we will take a picture and we will get an image of that point with the camera on the robot. That using image processing we can get the pixels of that point on the floor. Now our next step is going to convert from the pixels to the image coordinate system that we will represent an xi and yi. This is, I want to highlight that here we don't have depth, right? We don't have that. We don't know how far the point is from the camera. Our next step is about the detection of the point in the camera coordinate system. We can draw the camera coordinate system, and now we have a point in the space. We now have included this, how far the point is. For that, we will combine the information of the image and also the information of the ground. And finally, in our last step, what we define is like the coordinate frame of the robot, and what we want to know is what's the position of the point that we detected in the coordinate frame of the robot, and that's basically doing a transformation from the camera coordinate system to the robot coordinate system, and the result will be the vector of 3 elements in the robot coordinate system. I want to highlight that all this process and all what we do is like going from a point in an image that is simply a 2D point, and we combine the information of the ground and the image to obtain a point in the three-dimensional space that in this case will be represented in the robot frame. Okay, so let's come back to our robot sketch, and our robot detects a point on the ground. When we take the picture, our point is there, right? After applying some image processing, we will see a point that will be in pixels. In the pixels, we can see that we have a coordinate frame in the image that we will be denoted as u and v. So our point, we will have coordinates u and v, right? And this is a point in pixels. The way that we convert that point to the image coordinate frame is very simple. We just have that x in the image plane will be the value in pixels minus the width of the image over 2, in the coordinate y will be equals to v minus the height over 2. In that case, we will center the coordinate frame to the center of the image. The only issue that we have here is that we don't have the z-axis, right? We don't know about the z-axis. Now that we have a point in 2D, we will combine it with the information from the ground to obtain a point in 3D, and that point will be represented in the camera coordinate system. This is our next step. Let's study the perspective projection. We start with a camera. Let's sketch the camera, and we have a point that is detected by the camera. Let's draw the axis of the camera coordinate frame, and now we have the coordinates of that point in that camera. This is the projection of the point into the camera, and that point passes through the image plane. That is where the point is projected. From the image plane to the focal point, we have something that is called the focal length, that distance from the image plane to the focal point. And we will have that the z coordinate of the projected point will be equal to the focal point. So now we know we have the information of the z-axis and the y-axis in the image. However, we don't have yet the information in the space. There is a property using the similar triangles that this triangle is similar to this bigger triangle, and the property is that the sides of the triangle maintain the proportion while they scale. In this equation, there are some values that we know. For example, the y coordinate comes from the image. The f value comes from the camera parameters. Those values come from the camera calibration. However, there are still two values that we don't know. For that, we need to combine the information from the perspective projection and the ground. So we take a picture with the robot. And now let's trace a line that goes through the y-axis of the image. Let's project that line on the ground, and we will have 2 points, 1 point here and 1 point here. Let's name it P and Q. Those points will be shown in the image as P and Q. The line that we projected on the ground can be shown in the perspective projection. This line follows an equation that is basically that y depends on the coordinate of the z-axis and two constants that we don't know yet. Combining these two equations, we can obtain the z coordinates and the y coordinates. This can be done just by simple operations. However, we still don't know A and we don't know B. All the other values like the coordinates of the point in the image plane and the focal length are known. In order to obtain A and B, we need to define the robot coordinate frame, where we have the point P and the point Q. The camera has an orientation with respect to that frame that can be represented by a rotation matrix between the frame R and the camera, and we also have a translation that will represent as a point in the robot frame. Since the y-axis of the robot frame and the x-axis of the camera frame are aligned, if we know the tilting angle of the camera, we can obtain PR and QR by simple geometry using the field of view that we can write down like this, and we can represent as phi. And this will be the field of view angle that comes from the camera parameters. The points P and Q in the camera frame can be obtained using the information that we already know. Using these 2 points and the equation of a line in 3 dimensions, we know that the line in the camera frame, or all the points in the camera frame, will be equals to a parameter t times the difference of the points plus qc, and t is just a real parameter. When we place all the values on the equation of the line, we will obtain that the x-axis is 0 because the line were passing through the y-axis. So we have only values in y and z. Since this is a 2x2 matrix, we can obtain the parameters the parameters a and b just by solving these equations. From the perspective projection, we had that xc over zc is equals to xi over f. Now we can solve this for xc and replace zz by the value that we already obtained. And we can combine this result with the other 2 coordinates that we already have, and we obtain that the coordinates of the point in the camera frame. In our pipeline, we finally obtain the coordinates of the 3-dimensional point in the camera frame. Now, for our last step, we just need to convert that point to the robot coordinate frame. Converting the point from the camera frame to the robot frame is pretty simple, and we have done that before. This is simply using the equation of the transformation, that is c plus r, the rotation matrix that transforms from the robot to the camera, and the point pc. And finally, we got our point in the robot coordinate frame. The interesting part of this is that now we can detect multiple points at the same time, and we can project them in the robot frame. So now we can get a better idea of the street, and it can be used to improve the behavior of the robot. So, for example, what happens if the robot doesn't want to go in front of the line? The robot wants to follow a special path, like it wants to go parallel to the line, then it wants to cross it, then it wants to cross it again, or it wants to move in curves. And all of this can be done because the robot will know the line, the dashed line, and how the path is traced. Additionally, we can use it to map the streets of the environment, and we will see that in the following sessions.